Hi there, my name is Akshay and this is my Lab 5 video. The purpose of Lab 5 is to better understand and visualize Faraday's law. This lab had two parts to it, an experiment and a computational model. The experiment itself was pretty straightforward. We dropped a magnet through a tube of aluminum foil 5 times and recorded the average time it took for the magnet to leave the tube. Here are the physical principles involved with the lab. The first principle is that moving objects can induce currents in conductive objects. When we dropped the magnet through the aluminum tube, we induced a current in each small ring of thickness dy. We also have Faraday's law, which states that the EMF is equal to the negative change in the flux. The other principles are Newton's second law, the principle that if an object is moving with constant velocity, it has zero net force acting on it, and Newton's third law, which basically means that the magnetic force the magnet exerts on the tube is equal to the magnetic force the tube exerts on the magnet. Great, so here are my results and observations. Based on my 5 trials, I found the average time it took for the magnet to stay in the tube was 1.06 seconds. The magnetic moment that I got from my Lab 3 data was 1.53 amp meters squared. I believe that this value that I got was too small, and I'll discuss that a bit later. Also, I saw that the magnet appeared to fall at a constant velocity in the tube. Alright, so let's discuss the computational model. The goal here was to use the physics principles from earlier to find the net force on the entire tube and model the motion of the magnet falling through the tube. We first broke up the tube into a series of rings with thickness dy. The magnetic force on one ring was found from the equation I times delta L cross B, and I was found by taking the absolute value of the change in flux and dividing by resistance, or in other words, Faraday's law divided by resistance. By finding the magnetic force on one ring, we could find the magnetic force on the entire tube by the magnet, which would be equal to the magnetic force on the magnet by the tube from Newton's third law. Also, after calculating the force of gravity on the magnet, we can now model the motion of the magnet by considering the velocity of the magnet for different times, now that we know what F net is from F magnetic and F gravity. Looking at the results of my model, I found something interesting. When I used the mu value that I got from Lab 3, my time was very small and my graph did not have the correct shape. However, when I modified the magnetic moment to be about 4.3, I got a time close to my experimental value and I got a more accurate looking shape. This is why I believe my magnetic moment that I got initially was too small, and I believe that 4.3 is a more accurate value. My interpretation of the simulation are as follows, assuming that the mu value is around 4.3, since I believe my actual magnetic mu moment is around this value. The blue color represents counterclockwise current and red represents clockwise current. When the magnet is flipped around, the same motion and time can be expected, but the currents are going to be flipped. Also, time in the tube for the real-world system is less than the computational model, which can be made more accurate by accounting for air resistance, making the slice thickness closer to 0, and accounting for how a magnet would leave one's hand. Finally, the shape of the velocity versus time graph shows that just gravity acts on the magnet when it's initially dropped. Then we have zero net force while the magnet is in the tube, because of which we can see with the constant velocity, and then just gravity is acting on the magnet as it leaves the tube. Let's consider some questions. First, why can't we use a ferrous metal? We can't use a ferrous metal because the magnet would not fall through the tube and would get stuck to the side. What if the resistivity of the conductor were reduced as close as possible to 0? In that case, the current in the tube would be very high and the magnetic force would dominate gravity, meaning that the magnet would not be able to fall through the tube. In fact, I observed this when I set the resistivity to be 5 times 10 to the negative 10 ohm meters. And last, what if holes or slots were cut into the tube? We would have different cross sections and the overall current through the tube would be less from less current in each of the rings. To wrap up this lab, we visualized Faraday's law both computationally and experimentally. The computational model had differing times from the experimental data, as it did not account for certain factors like air resistance. Overall, I think that my model confirmed what I saw when corrected for the magnetic moment, but I would need to experiment further to determine what my exact value for the magnetic moment should be. Okay, that's the end of my video. Thank you guys for watching.